Now we're going to look at 4 examples of Newton's first and second law. We have 4 examples. The first one, you'll be given the forces and mass and you will need to find the acceleration. That will be an application of Newton's first law, which means that an object will carry on at a constant velocity until acted on by a force. So in other words, the force is 0. Then you will give the second example, which you will be given the forces and the mass. You will need to find the acceleration. This is an extension of Newton's first law to the case where there is acceleration. The forces are not balanced and we will have an acceleration. And we need to find that acceleration. The third example is that you're given one force, you're given the mass and the acceleration, and you must find the other force. So it's kind of working the last section backwards. The last one is much more complicated. You're given the weight, you're given the mass and the acceleration, and you basically have to find the component of the weight which is acting down the slope, and then you need that to find the other force. So Newton's first and second law. When you do this, first you must determine the size and the direction of the forces. You must draw a free body diagram because that will help immensely in solving these problems. Once you have the free body diagram, you need to add the vectors to find out what the resultant force is, the net force. If the vectors add up to 0 or they cancel out, that's a case of Newton's first law. So it will continue at a constant velocity, 0 acceleration. So the velocity is constant or it will be motionless. The second one, if the vectors add up to a non-zero force, then this is a case of Newton's second law. An unbalanced force will give an acceleration according to the equation F equals m times a. So if you know the unbalanced force and you know the mass, you apply F is equal to ma, rearrange to make a the subject is equal to F divided by m. Right, let's have a look at the first example. In the top right hand corner we have a reminder of what we need to do. We have a tandem sky jumper. We have a tandem skydiver who's jumping from a plane. The mass, or the combined mass of the two jumpers, is 140 kilograms. The air resistance, we are told, is 1400 newtons. And you need to find the acceleration. There they go. So the first thing is to determine the size and the direction of the forces. Now the force down is equal to the weight, mg. The mass is 140 times by 10, which is 1400 newtons. The force up is equal to the air resistance, which is also equal to 1400 newtons. We need a free body diagram. Here is the tandem jumper. The force down is equal to 1400 newtons. The force up is also equal to 1400 newtons. Notice that these two arrows have the same length to show the same size force but in opposite direction. The third thing you need to do is to add the vectors. Let's add these two vectors. 1400 plus negative 1400 is equal to 0 newtons. Now these forces add up to 0, therefore the net force is equal to 0. If there's no force, the acceleration is 0, which means we have a constant velocity. This will be, in this case, the terminal velocity of the jumpers. Example 2. Now, the tandem skydiver jumps from the plane and the parachute opens. So the forces are going to change. The mass is still 140 kilograms. The air resistance is now 2,100 newtons. What is acceleration? Right, point 1, determine the size and direction of the forces. The force down is still the same, mg 1400 newtons. The force up, however, is 2100 newtons. Free body diagram. The force down is the weight, which is still 1400 newtons. Now the force upwards, notice that the arrow is larger, is equal to 2100 newtons. Now we must add the vectors. 2100 plus negative 1400 gives 700 newtons up. So the forces add up to 700 newtons, an unbalanced force, and this is a case of Newton's second law. F equals ma, rearrange to find the acceleration. And we have the acceleration is equal to 5 meters per second squared. Example 3. We have a 3 kilogram bunny rabbit who slides down a slope and accelerates at 2 meters per second squared. The amount of friction is 4 newtons. Find the force that is pulling it down the slope. Now we know the mass is 3 kilograms. The friction which is going up the slope is 4 newtons. Find the force or the effect of gravity pulling it down. Determine the size and direction of the forces. Now the force down is the value we want to know, so we have to leave that as a question mark, or x. The force up is 4 newtons. This is the bunny rabbit. There's a force down, which we don't know, which is a component of the weight. The downwards force, we need to find that. And we have a smaller force upwards, which is 4 newtons. Now we add these vectors, but we don't know what the downward vector is. So 4 newtons up plus the negative force downward basically gives the unbalanced force, which is acting down. But we know this unbalanced force will provide the acceleration. The acceleration is 2 meters per second squared. The mass is equal to 3 kilograms. So we know that 4 newtons plus negative x newtons gives negative 6. So there's an unbalanced force downwards of negative 6. So how much must the downwards force be to give an unbalanced force of negative 6, given that there's 4 newtons already pulling up the slope? Well, it's 4 minus this force is equal to negative 6. This gives a downwards force of 10 newtons, which is basically an unbalanced force of 6 newtons down the slope, which provides that acceleration. The last example is the most complicated. We have another rather fat 6 kilogram bunny rabbit which slides down the slope at constant velocity. The slope is inclined at 30 degrees to the horizontal, so you must calculate the friction. Now the mass is 6 kilograms. The friction is an unknown value. First thing, find the force of or rather the effect of gravity pulling down the ramp. Now we don't know this force, but we do know the weight. And then from that we find the effect of friction. Because if it's moving at constant velocity, the friction must be equal to the component of weight acting down the slope. Here's the giant 6 kilogram bunny rabbit. Now we know its weight is downwards, mg. It's 6 times 10, which is 60 newtons. There's also a force upwards, which is the effect of friction. These are the only forces that we are concerned about here. There's also reaction, but I haven't drawn that. What we do need to know is what is the component of the weight acting down the slope. So we need to find the normal to the slope. And what is this component here? Well, if we know that this angle here is equal to 30 degrees, we know this angle here is 90 minus 30, so this angle must be 30 degrees. And we're finding the opposite to this 30 degree angle. That's going to be sine. So the opposite is 60 times by sine 30. So let's determine the size and direction of the forces. The component of the weight acting down the slope is 60 sine 30. What is the force acting up the slope? Well, we don't know that yet. Let's add the vectors. What do we know about the vectors? Well, we know that we have a constant velocity. So this is a case of Newton's first law. The forces must be balanced. So the friction, the force up, plus the force down, which is 60 sine 30, which is equal to the resultant force, must be equal to 0, because we know the forces are balanced. So A must be 0. We know that, the constant velocity. So therefore the friction must be 60 sine 30, but only because these forces are equal, because there is no acceleration. And that concludes the 4 examples that I wanted to show you.